let's get started. So with 3.1, we introduced the concept of a derivative. With 3.2, you're mostly focused on calculating a bunch of derivatives by hand over and over again, right? So with 3.3, now we're going to start discovering differentiability rules for calculating derivatives, so that we don't have to calculate it by hand over and over again. So we're going to come up with some basic rules, some basic patterns to look for to help us calculate derivatives. So the first one that we're going to look at is the derivative of a constant, any constant. What is that? So we're going to do f of x is just equal to some constant c. So what is the derivative of this? Doesn't matter which form we use. I'll use the limit as x approaches x naught f of x minus f of x naught all over x minus x naught. Now before we actually solve this, let's just use our intuition for a second. What do we expect the derivative of this function to be?
C. Constant.
A constant?
Yeah.
What does a constant function look like?
Just straight.
Just a horizontal line. And intuitively, what does a derivative give us?
It'll give you the slope.
What's the slope of that line?
Oh,
0. So we expect this to come out 0.
Yeah.
Okay. So let's work with it. So this is equal to the limit as x approaches x naught. What's f of x equal to? C. What's f of x naught equal to?
C.
What's c minus c?
0. 0. Okay.
So, derivative of constant, 0. All right. Let's see which one they want to do next. Okay, so next, I want to do a little bit of algebra, which would help with the problem that you got stuck on, and then we'll do the next group. Here's what the algebra problem is that we're going to do. I'm going to take a minus b, I'm going to multiply it by a to the n minus 1 times b to the 0 plus a to the n minus 2 times b to the 1 plus, I'm going to keep going in this pattern, decrementing a and incrementing b. So I'm going to write out one more term right here, a to the n minus 3 times b squared plus dot 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 plus our second to last term would be a to the 1 times b to the n minus 2 plus a to the 0 times b to the n minus 1. Let's multiply this thing out and see what we get. But do you understand what this is saying?
Not really.
So n's just going to be some positive integer like 5.
Okay.
Let's do a very concrete example, then we'll do it in the abstract. Maybe that will help. So let's come over and do a minus b times, we'll do, keep it simple for now, a squared times b to the 0 plus a to the 1 times b to the 1 plus a to the 0 times b to the 2. So in this case, my n is 3.
Okay.
Plug in 3 for n here, we get 2 and 0. And then from there on out, decrement the exponent on your a's and increment the exponent on your b's until this has the same powers that this has.
Okay.
And let's multiply this one out really quick and see what we get. Rewrite it one more way. I was just writing it that way to help you see the pattern very explicitly. So this is the same as a squared plus a times b plus b squared, right? Okay, so let's multiply this out. Let's distribute the a through and see what we get. When I distribute the a through, I'm going to get a cubed plus a squared times b plus a times b squared. That's distributing a all the way through that.
Yeah.
Now I'm going to distribute the negative b through it. When I distribute the negative b through it, negative b times a squared, I'm going to get negative a squared times b, negative ab squared, minus b cubed. You see all that? Now, add all those together, what do we get?
A cubed minus b cubed.
A cubed minus b cubed. So it was equal to a to the n minus b to the n. Because n in this example was 3. So when we multiply this whole thing out, the same thing should happen. So let's multiply this out and see what we get. A times a to the n minus 1 is
A to the n.
a to the n. A times this term gives us a to the n minus 1 times b, right?
Times that, yeah.
Plus, multiplied by this term, we get a to the n minus 2 times b squared, plus dot dot dot, plus a squared times b to the n minus 2, plus a to the 1 times b to the n minus 1. That's distributing through the a.
Okay.
Distributing through the b times this, we're going to get negative a to the n minus 1 times b. You see that? And we'll get negative this term, negative this term, negative this term, negative this term, a to the 1 times b to the n minus 1. So that was multiplying b into this term. It's right there, right? Finally, minus b times this term gives me b to the n.
Okay.
Everything cancels out once again, except for the a to the n and b to the n. So this is equal to a to the n minus b to the n. Very useful factoring formula. Anytime you're solving a problem and you get two terms with the same exponent, that is a very good thing. You can instantly factor it like this. So going back to the problem you were doing x to the 3/2, right?
Yeah.
So we were trying to figure out the limit as x approaches x naught of x to the 3/2 minus x naught to the 3/2 all over x minus x naught, right? And so we can rewrite this as the limit as x approaches x naught of the square root of x cubed minus the square root of x naught cubed all over square root of x squared minus the square root of x naught squared.
Okay.
Now you see how both these fit this formula.
Yeah.
And so I can factor a minus b, or in this case, square root of x minus the square root of x naught out of both these terms. So this is going to be equal to, start with the numerator, we're going to be factoring out the square root of x minus square root of x naught, and that's going to be times, follow our formula, our n is 3, so we need an a to the 2, right?
Yeah.
And then we need a plus an a to the 1 times a b to the 1 plus a b to the 2.
Yeah.
Okay? And then in the denominator, this is just perfect square. So this one's square root of x minus square root of x naught. In this case, n's 2, so inside we're just going to have a 1. just have that term and that term. Does that all make sense?
Since you're squaring each of the individuals and they're just subtract, why do you get the plus
On the inside?
on, yeah, right there?
Notice that all the terms in here are positive.
Oh. Okay.
So once we factor out negative, all that's left is positive terms. So we started with difference and a difference. We factor out a difference, leaving just a large sum after that. Okay. And now, I think you see how you continue with this problem, right?
You just keep going. Oh. You just solve it. Write it down.
Well, now we can cross this out with this out.
Yeah.
And now our denominator is not going to 0 anymore.
Okay. So that's the answer.
So now we can take our limit. So this is equal to the limit as x approaches x naught of this whole thing. So square root of x squared, that's the same thing as just x now. X plus the square root of x times the square root of x naught plus x naught all over the square root of x times the square root of x naught, right? Oh, thank you. Good? Okay, so now we can take our limit. And our denominator is not going to 0 anymore, so we're good. Notice this was the term that was going to 0.
Yeah.
So, take our limit now. As x approaches x naught, x gets closer and closer to
X naught.
x naught. So we have x naught plus the square root of x naught times the square root of x naught plus x naught all over the square root of x naught plus the square root of x naught.
Okay.
So this is equal to, we have x naught plus x naught plus x naught, right?
Yeah.
So we have 3x naught in the numerator. And in the denominator, we have 2 square roots of x naught. Last thing we can do is cancel the square root of x naught out from top and bottom. So this is equal to 3 square roots of x naught over 2. This is equal to 3 times the square root of x naught times the square root of x naught over 2 times the square root of x naught,
And you just got it one.
and cancel, cancel.
Okay.
Good?
Yeah.
Okay. So now that we did it the hard way, teach you the formula for how to do these the easy way. And we'll be using this algebraic formula here. So we want to figure out, so if f of x is equal to x to the n, x to any integer power, what's the derivative?
Okay.
So pick any number you want right there, plug it in, what's the derivative? That's what we're figuring out. So f prime of x is equal to the limit as x approaches x naught of x to the n minus x naught to the n all over x minus x naught, right? Now you see how this formula is going to help us. We're going to factor an x minus x naught out of this thing, cancel it out top and bottom. see what's left, take our limit. Okay. So this is equal to the limit as x approaches x naught of x minus x naught, factor that out of the numerator. That leaves us with x to the n minus 1 plus x to the n minus 2 times x naught to the 1 plus x to the n minus 3 times x naught to the 2 plus etc. Plus x times x naught to the n minus 2 plus x naught to the n minus 1. Follow that?
Yeah.
Okay? And then our denominator is x minus x naught. So we can cancel out that with that, and then just take the limit of this thing. Right? So when we take that limit, what do we get?
A bunch of x naughts.
Yeah, replace all our x's with x naughts, right?
Yeah.
So my first term is going to be x naught to the n minus 1 plus, what's my second term going to be?
X naught to the n minus 1.
X naught to the n minus 1. What's my third term going to be?
X naught to the n minus 1.
Exactly. They're all x naught to the n minus 1 plus x naught to the n minus 1. That's what they all are.
Okay.
So now the last question is, how many of these terms are there?
How many n is?
N, right?
Yeah.
There's n in these terms. So this is equal to n times x naught to the n minus 1.
Okay.
That's f prime at x naught. What does that mean? If you're looking at x to the n, want to take its derivative? It's just n times x naught to the n minus 1. So now you can do this in your sleep. If I say f of x is equal to x to the 6, then f prime of x is equal to 6 times x to the 5.
That is so low.
Now, the way that we proved this, we only proved it for positive numbers n there. Turns out it works for any real number. So, if f of x is equal to x cubed, or x to the 3 halves,
Yeah.
then f prime of x is equal to 3 halves, whatever your exponent was, bring it down, and subtract 1 from it, times x to the 1 half. Or, exactly what we had before, 3 squared of x over 2.
Okay.
Let's do another one. What if f of x is equal to x to the pi? Then what's f prime of x?
Just pi x and then pi minus 1.
To the pi minus 1. That's all there is to it.
Okay.
Did one like that. Let's do one with negative exponents real quick. If f of x is equal to 1 over x to the 4, what's f prime of x?
Just 1 over 4x to 3.
No. So we have to get this in the numerator to apply our rule.
Okay.
So how do we get the denominator turned into the numerator? Remember this, you need to make the exponent negative. So this is the same thing as x to the minus 4. Does that ring a bell? Ish?
Yeah.
Well, that's what negative exponent means.
Okay.
So this negative exponent means this thing. So when you have them in the denominator, put them in the numerator, make the exponent negative.
Okay.
Okay, so now, what's the derivative?
Just negative 4x to the power of negative 5.
Times x to the minus 5. Perfect. Or if you want to rewrite it how it was before, then you can say negative 4 over x to the 5. Whatever you like more.
Okay.
Intuition for negative exponents, being the same thing as exponents down here, give you some quick intuition for that. When you multiply terms together, you add the exponents, right?
Yeah.
So if I do x squared times x to the minus 2, that's equal to what?
0.
X to the
1.
0, which is equal to 1,
Yeah.
right? Well, notice that x squared over x squared is also equal to 1.
Okay.
So putting a term in the denominator cancels out with the numerator, just like a negative exponent cancels out with a positive exponent. Okay. Next one. So, next thing I want to prove is that, what's the easiest way to say it? Here's how the author writes it, so I'll just write that way. The derivative with respect to x, throw in some more notation, some of that notation to help me keep seeing it. The derivative with respect to x of a constant times some function u is equal to c times du dx. In other words, we can pull constants out and then take our derivative.
Okay.
That's what that's saying. So let's prove it. So, we don't know anything about u. All we know is that u is some function.
Okay.
So, some function u of x. So then the limit as, we'll go back to some of the author's notation, the limit as h approaches 0 of c times u of x plus h minus c times u of x all over, let's see, h. So that's the derivative of this function, right?
Yeah.
Okay. So this is equal to, notice I can factor c out of the numerator. So this is the same thing as the limit as x, as h approaches 0 of c, pulling c out of the whole thing, times u of x plus h minus u of x all over x, not x minus, all over just h, right?
How did you pull the c out of the numerator?
I factored it out.
I mean, completely out of the fraction. Isn't it c over h?
1/2 times 6 over 3 is the same thing as 1/2 times 6 over 3. You can pull terms in the numerator all the way out, factors in the numerator all the way out. Okay. So now, we already know from our limit rules, remember this is still just a limit,
Yeah.
and I already know from my limit rules that I can pull my constants out of my limits. And doesn't change anything. So this is the same thing as c times the limit as h approaches 0 of u of x plus h minus u of x all over h, right? And I don't know what this is, but it's the derivative of u.
Yeah.
So this is equal to c times the derivative of u with respect to x.
Okay.
Should have started by saying the derivative with respect to x of c times u is equal to that, is equal.
Okay.
Right? Okay, so we showed that one. So you can pull constants out. So what does that mean? That means that if we're looking at f of x is equal to something like 6 times x to the 5, you know how to do it when it's just x to the 5, right?
Yeah.
So you can just pull this 6 out and then multiply it in later.
Okay.
So what's the derivative of this then?
It would just be 6 times 5x to the power 4.
So 30 times x to the 4. Correct. Okay. So now, our next one. Well, maybe we'll do his examples here real quick. We already did a harder example. Okay, so don't do that one. The derivative of negative. Derivative of the negative of differentiation. Okay, we already did a better example, so we won't bother with his, and we'll go on to the next row. The next row. So we're going to say u and b are functions here, they're not constants. I'm going to show that the derivative with respect to x of u plus b, so the derivative of the sum is equal to the sum of the derivatives. U and b are functions here.
What does that look like in a problem like over there?
So let's do a concrete example real quick using this rule. Let's say that I have 3x squared plus 7x, and I want to take the derivative of it. Then it would just be 6x plus, what's the derivative of this? 7. Good job. So that's what this rule says.
Okay.
Okay. So let's prove the rule. So the derivative with respect to x of u plus b is equal to the limit. This time we'll just use x approaches x naught of, we have u of x plus b of x minus, maybe I'll put brackets here to help keep our plugging in very clear, minus u of x naught plus b of x naught all over x minus x naught. Follow that?
Yeah.
Okay? So, this is equal to, just going to reorder the terms in my numerator. So I'm going to write this as, the limit as x approaches x naught of, we have u of x minus u of x naught plus v of x minus v of x naught all over x minus x naught. Follow that? Just reordering the terms in the numerator.
Yeah.
Now I can split the fraction in two. So I can write this over x minus x naught and this over x minus x naught, right? Okay. Now going back, no, move the plus sign down here. Now going back to our rules with limits, we know that a limit of a sum is the sum of the limits. So I can break this up into two separate limits.
Yeah.
Okay. So this is equal to the limit as x approaches x naught of our first term, u of x minus u of x naught all over x minus x naught plus the limit as x approaches x naught of v of x minus v of x naught all over x minus x naught. Right?
Yeah.
Now take the limit. What is this limit? It's just a derivative of u. We don't know what it is, but it's the derivative of u.
Yeah.
So whatever it is, it's the derivative of u. It's the derivative of u with respect to x, u dx.
Okay.
Similarly, what's this?
Derivative v.
Derivative of v. So we just really show the derivative of a sum is equal to the sum of the derivatives.
Okay.
Make sense?
Yeah.
So now with that, we can take the derivative of any polynomial function. Because polynomial functions are just going to be constants times a term to some power. Add it up.
Okay.
We figured out how to work with the constants in the front. We figured out how to work with the x with its exponent. And we figured out how to deal with sums. So now if I write pi times x to the 8 plus root 2x squared minus 1. Here's f of x. Let's take that derivative. So what's f prime of x then?
It would just be pi times 7x.
8.
Pi times 8 to x.
So we have 8 pi times x to the 7, right?
Yeah.
Plus
Square root of 2 times 2x.
2 root 2 times x.
Minus 1.
No, remember the derivative of constant is 0.
Okay.
Good?
Yeah.
All right. Okay, so now here's an interesting question. A little bit of applications of derivatives. Remember, derivatives keep in derivatives capture the slope of a function, right? Always keep that in mind. So the next example is, does the curve y equal x to the 4 minus 2x squared plus 2, does this function have any points tangent to 0? Where is there anywhere where the curve, the slope of this function is 0? That's the question we want to answer.
Okay.
So we have no clue what the scene looks like. The question is, are there places where the slope is equal to 0?
Okay.
So that's equivalent to saying, are there places where the derivative is equal to 0? Right? So let's figure out the derivative real quick. So what is the derivative of y with respect to x in this scene now?
It'd be 4x power 3 minus 4x. Yeah.
And that's it, right? So now, factor this in. This is equal to factor 4x out. And what am I left with?
X power 2 minus 1.
X squared minus 1. Now, where is this thing equal to 0? Well, we can factor that perfect square.
Yeah.
Remember, 1 can always be viewed as 1 squared. So this is equal to 4x times x minus 1 times x plus 1, right?
Yeah.
So now, where are all the places where this is 0?
Yeah. 1 and negative
1, negative 1. Anywhere else? Where is this term 0?
1. That's 0.
0. So there's 3 places. So whatever this function looks like, it has a slope of 0 at 1, negative 1, and 0.
Okay.
Make sense? 0, 1, negative 1. Okay, we did it right. Okay. So we show that the derivative of a sum is equal to the sum of the derivatives. What about the derivative of a product? So now we want to look at the derivative with respect to x of u times v. What do we think that's going to equal?
Derivative of u times the derivative of v.
Well, let's see what it equals. So, we're looking for the limit as x approaches x naught of u of x times v of x minus u of x naught times v of x naught all over x minus x naught, right? Okay. So, let's go over and look at this. So, what can we always do to our expression? We can either add 0 or multiply by 1. I'm going to add 0 to the numerator. Here's the term I added and subtracted. The 2 middle terms.
Okay.
See it?
Yeah.
Okay. So now, I'm actually going to split this into 2 fractions. I'll move this plus down. So x minus x naught, and x minus x naught. And then, over here, I'm going to factor v times x naught out. And over here, I'm going to factor u of x out. Okay, so this is equal to the limit as x approaches x naught of, we're going to have u of x times v of x minus v of x naught all over x minus x naught plus v of x naught times u of x minus u of x naught all over x minus x naught, right? And now we can take our limit. What's the limit of u of x as x approaches x naught? u of x naught,
Okay.
right?
Yeah, okay.
All right.
But you still have 0 denominators.
I do. I still have things going to 0 in my denominator, which is a problem when I'm trying to calculate exactly what the derivative is.
Okay.
But this right here is the derivative of v, right?
Yeah.
So we're assuming, sorry, I probably should have said this before. We're assuming that these are both differentiable. That's our assumption.
Okay.
So, whatever this is, we already know what this number is. Whatever it is.
Yeah.
Okay, so what's this right here?
The differential of v.
Yeah, that's going to be v prime at x naught, right?
Yeah.
And then over here we get plus, as x approaches x naught, v of x naught is still just
That's not.
v of x naught. And then we have times, what?
Prime of x naught. U
U
of x.
prime of x naught. Right?
Yeah.
So, so notice that it was not just u prime times v prime. It wasn't just product of the derivatives. And the way that here's the way that we actually usually write it. I'll write the exact same thing, just different notation now. So the derivative with respect to x of u times v is equal to, the way we typically remember it is du dx multiplied by u, or multiplied by v, plus dv dx multiplied by u. All the same things here. Du times v, that's this term,
Okay.
plus dv times u. And the way we memorize it is the derivative of a product is equal to the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Okay.
So when you have two functions that you're multiplying together and you want to take their derivative, then we can do it that way. So let's do an example using this and make sure we understand it. So let's say y is equal to x squared plus 1 times x cubed plus 3. Now notice that you have two choices on how to solve this derivative. You could factor it all out, then you just have a polynomial, and then take the derivative the way that you already know how.
Yeah.
The other way that you can do it now is to use this formula.
Okay.
Let me write the formula one more different way, just to, maybe this will help also. So the derivative with respect to x of f times g, the product of two functions, is equal to f prime of x times g of x plus g prime of x times f of x. Same thing, right? Okay, so let's calculate the derivative now. So y prime is equal to the derivative of the first function. We're just arbitrarily going to call this thing right here f and this thing right here g, right?
Okay.
So the derivative of this is,
X. Right?
what's the derivative of this?
2x.
2x, perfect. So the derivative of the first multiplied by the second plus the derivative of the second,
Which is just 2x cubed. No, 3x squared.
3x squared, perfect, times the first.
Yeah.
There's our derivative. And then you can multiply it out, but that's the derivative.
Okay.
So that's how the product works. works.
Okay.
And then our last major rule is called the quotient rule. So this is for when you have a quotient of functions rather than a product of functions. So let's see what that gives us. So let's look for the derivative with respect to x of f of x over g of x. Well, f over g is really how we write it, the x is there. Right?
Yeah.
Okay? So this is going to equal the limit as x approaches x naught of, we're going to have f of x over g of x minus f of x naught over g of x naught all over x minus x naught. Right? Let's get a common denominator in the numerator. So this is equal to, I'm multiplying this top and bottom by g of x naught, and this top and bottom by g of x. So this is equal to f of x times g of x naught, that's this term, minus f of x naught times g of x all over g of x times g of x naught all over x minus x naught. Okay. Oops, got my limit. Now, first thing to note, when we divide by a number, that's the same as multiplying by its reciprocal. So this is equal to limit as x approaches x naught of I'm also going to pull, that might be too much algebra, we got, let's just do this one step at a time. F of x times g of x naught minus f of x naught times g of x all over g of x times g of x naught times x minus x naught. Right?
Yeah.
Okay. So now, I'm just going to take 1 over g of x times g of x naught and just pull that clear out front. Not outside the limit, but just outside my fraction to help you see things. So x approaches x naught, so we'll do 1 over g of x times g of x naught times this thing now. F of x times g of x naught minus f of x naught times g of x all over x minus x naught. Just pulling these two terms out.
Okay.
Good with that?
Yeah.
Okay. So now, that's starting to look like something we can work with, right? Let's see, what am I going to want to plus and subtract from that to make this work? You want f of x times g of x? Let me try that and see if it works. So I'm going to add and subtract f of x times g of x in the numerator of this thing. And I think that will give me what I want, so I can split it into two and take derivatives. So this is equal to the limit as x approaches x naught of 1 over g of x times g of x naught, all times. So I'm going to add and subtract f of x times g of x. So here's my first f of x times g of x, the one that I'm adding. And now I'm going to write this term. So plus f of x times g of x naught. Now I'm going to minus my f of x times g of x. And then I'm going to minus this term. See how I just add 0?
Yeah.
Okay. Now we can split this thing into two. Over here, I'm going to factor out an f of x. Over here, I'm going to factor out a negative g of x. Okay. So this is equal to the limit as x approaches x naught, 1 over g of x times g of x naught times brackets here, since I'm going to split this into two, this has to multiply to the whole thing. So we're going to have these two terms. I'm factoring out the f of x. So f of x times g of x plus g of x naught over x minus x naught. Ooh, plus. That doesn't work. Sugar. That means I chose the wrong thing to plus and minus. You need an f of x What if I would factor out a negative? Sorry, I just need to think for a second. I'm thinking if I factored a negative out of this thing, make that negative 1, make this negative, that positive. You with me? Okay, let's not actually mess with this. No, I'll just write up here. If I factored a negative out there, then we'd have negative f of x times g of x naught plus f of x naught times g of x. Okay, so now you need to be subtracted from an f of x times g of x naught, or g of x. So that, subtract that would work. Then over here we have negative f of x naught, negative f of x times g of x. negative 1. Negative 1 times, that's going to make this term negative, this term positive. So then I'm going to have my first f of x times g of x. This is one term I'm adding in, minus f of x times g of x naught. That's this term multiplied by 1. And then I have my second, minus f of x g of x, plus that. So minus f of x times g of x, and we have plus plus this. Okay, I think we might be on track there. Probably should have just looked in the book at what they were doing. You see where all the terms are?
Yeah.
So this and this cancel out. This is our first term there, now negative since we factor out negative 1. And this is that term there, now positive because we factor out negative 1.
Yeah.
Okay. And we'll write this. It's two separate fractions, x minus x naught. This, we can't really do that since there's that minus there. It might confuse us. So we'll leave that all over 1 for now. Anyways, this is equal to the limit as x approaches x naught. Now let's split up into separate fractions. So writing this term now, factor out the f of x. Oh, we just first get my g's. 1 over g of x times g of x naught, all times, factor out my f of x, times g of x minus g of x naught, all over x minus x naught. So that's this term, right? Oh, we're going to need brackets here since we're going to split this into two separate fractions. So now I need to write this fraction. And I'm going to pull out a negative. So pulling out the negative is going to make this positive and this negative. So I'm going to write subtract instead of plus. So now we're going to have positive f of x times g of x plus f of x naught times g of x all over x minus x naught. Okay. Oops, probably should have done that at the same time. Factor out my g of x out of this, right? Taking g of x out, g of x out. Should have just done that. Let's just do that real quick. So also factoring out my g of x. So you can think about it as factor a negative g of x out of both these, if you want to think about it that way. Minus g of x times f of x minus f of x naught all over x minus x naught. Okay, now we're ready to take our limit, finally. Right?
Yeah.
What's g of x getting closer and closer to?
X naught.
G of x naught, and this is also g of x naught. So that's going to be 1 over g of x naught squared,
Okay.
right? Times, a bracket here. What's that?
That is f
F of x naught, right?
naught
Times
the prime g.
g prime of x naught.
X naught.
Perfect. Oops, that's a negative 1.
Subtract gx naught times f prime x.
Perfect. Now, putting this all together, distribute that negative back in. That's going to make this one negative and this one positive.
Okay.
So I'm going to write the positive one first. So we got g of x naught times f prime of x naught minus f of x naught times g prime of x naught all over g of x naught squared.
Yeah.
Good? Okay, so that's our derivative. So, the derivative with respect to x of g, or f over g, is equal to the bottom function times the derivative of the top minus the top times the derivative of the bottom all over the bottom function squared.
Okay.
Little mnemonic device that a lot of people use to memorize this. Low d high minus high d low. Low, the bottom, times d high, derivative of the top. Low d high minus high, the top, times d low. Square the bottom, and away we go. So that helps you remember it. So be it. Okay, so that's going to be our most complicated one that we do. So let's see this in action now and calculate the quotient. So we have, we'll calculate the derivative with respect to x of t squared minus 1 all over t cubed plus 1. T cubed plus 1. Right?
Okay.
So, let's figure it out. It's the bottom times the derivative of the top,
Yeah.
which is
2t.
perfect, minus the top times the derivative of the bottom,
Which is 3t squared.
all over the bottom squared. And then you can do the algebra of simplifying it.
Yeah.
All right, let's do one more, and this one will make a big example, and we'll actually work it all the way through, all the algebra of simplifying it all the way to the end. So maybe to help us keep track, the derivative with respect to x of f times g was equal to f prime of x times g of x plus g prime of x times f of x quotient. Low d high minus high d low squared to bottom. Okay. So the one that we're looking at is y is equal to x minus 1 times x squared minus 2x all over x to the 4. Okay? Let's see. I don't really want to use the product rule there. Tell me he just simplifies. Okay, he just simplifies that. We'll do it that way. We won't use both rules. Okay, so simplify the numerator real quick. Multiply the x through this thing, and we're going to get x cubed minus 2x squared. That's distributing the x through, right?
Yeah.
Now distribute the negative 1 through. We're going to get minus x squared plus 2x all over x to the 4, right?
Okay.
Which is equal to x cubed minus 3x squared plus 2x all over x to the 4.
Okay.
So now y prime is equal to, tell me what's right?
X to the power 4 times I 3x squared minus 6x plus 2.
Perfect. Minus
Subtract x, yeah, top
times
times 4x cubed
all over
x to the power 8.
perfect. Okay. Now let's simplify. First thing I'm going to do, before I mess with any of this, I'm going to factor an x cubed out. We won't do that. Never mind. We'll probably do it substitutive. So let's just distribute it through. So we're going to get now 3x to the 6 minus 6x to the 5 plus 2x to the 4. That's this term. We're going to get minus, notice, negative 4x to the 6. See that?
Yeah.
Plus 12x to the 5. See that?
Uh-huh.
And then minus 8x to the 4th. All over x to the 8. Which is equal to, add like terms, how many x to the 6's do I have in the numerator?
2. It'd be negative x.
Negative x. So I have negative 1 x to the 6's. How many to the 5 do I have?
6.
Positive 6. And how many to the 4 do I have?
6. Negative 6.
Okay, that's all my terms, right?
Yeah.
All over x to the 8. Now I can factor in x to the 4 out of my numerator,
Okay.
and then cancel it out with my denominator. leaving only 4x's down here. So see if you can follow this algebra. So that's going to be x squared when I get rid of 4, plus 6x when I get rid of 4, minus 6 when I get rid of 4, all over x to the 4 when I get rid of 4. Follow that?
Yeah.
And there's our answer.
Okay.
We could split it up more if we wanted to. The author does. I don't really like that, but since he does it, we'll write his answer. Splits us into separate fractions, so he writes this as negative x squared over x to the 4, plus 6x over x to the 4, minus 6 over x to the 4, which is equal to, now we can take 2 x's out of top and bottom, leaving me minus 1 over x squared, plus 6 over x cubed, minus 6 over x to the 4. Okay. And we got the same thing as him. Okay. Okay. Last thing we talked about in this section is the concept of taking higher order derivatives, which just means take the derivative again.
Okay.
So if I say y is equal to x cubed minus 3x squared plus 2, then y prime is equal to
3x cubed squared minus 6x.
right?
Yeah.
And y double prime. So now we're saying this is the slope of this function.
Okay.
And what's that derivative going to be?
6x minus x, not 6.
Just 6, right?
Just 6.
And what about y triple prime?
Then it's just 6.
And then after 3 primes, since we get sick of doing primes, if you do any derivatives after that, the way that we write it is y, and we do parentheses 4 and parentheses, so you know it's not an exponent.
Okay.
So the fourth derivative now is
0.
0, and the fifth derivative now is
0.
0. Good. So that's higher order derivatives and how we represent them. Okay, so that finishes 3.3, and that's about all I can handle today. So we'll call it there.